Good morning. My name is Vijay and I am presenting my stage show for the benefit of viewers on the experimental demonstration on quantum science in visible range. In fact, I have spent my time with the University of Rajasthan, where Professor D.P. Khandelwal was as a visiting professor, and he has inspired me to do physics through experiments, wonderful training which I got from University of Rajasthan with Professor Saraf. That is what I am narrating. So, in order to celebrate the Professor D.P. Khandelwal centenary year, in fact, he has been inspiration to IIPT, and he stressed upon quality education, and every time he used to talk about the physics through experiment concept, and has developed a very good leadership in the country regarding the physics. And we are having the IIPT started by him, and now we are having more than 8,000 members in the country throughout. In fact, when we talk about the centenary year celebration of quantum science, we cannot forget the name of Dr. C.V. Raman, Meghnad Shah, and S.N. Bose, who have contributed a lot for the nation and the fundamental science. And in fact, Raman effect was discovered during the same time, 1930. He was awarded a Nobel Prize, and he talked about the interaction of light with the atom. When Shah was working, Meghnad Shah, he talked about the interaction of light, how the light comes from sun and stars, and the Bose-Einstein was famous for the statistics and energy exchange phenomena in atoms and molecules. So during the stage show, I like to describe the quantum phenomena through the laboratory demonstration which we have designed and developed throughout our career, right from University of Rajasthan to other places like Vivekananda Global University, where I worked, and now I am working at Center for Innovation in Science Teaching at IIS University, Jaipur. So I will be talking about the atomic configuration, van der Waals potential, Rutherford scattering, Bohr orbital and Raman effect, alpha decay and molecular vibration, and plasma state. All these phenomena we can demonstrate using the laboratory experiment in the laboratory. Right now I got setup of only the two apparatus, one an harmonic oscillator and another one the Lorentz oscillator, okay, which demonstrates the kind of dynamics I will be talking about, the kind of interaction I will be talking about to describe all these phenomena. I got a vacuum chamber also where we can generate the plasma, and that is what is my laboratory. So in a limited time, I cannot explain working of each and every one, but I will share the videos which is collected here one by one. For example, when I talk about the molecular vibration, I got these balls, plastic balls, over which ring magnet is attached on each one. And when I play, then you can see the dynamics.
Ring magnet is attached on each ball with identical polarity of north-south, so that the dipoles are interacting. The balls are able to float on a surface of water, and they arrange themselves in a particular configuration. 7 ball with hexagonal symmetry, 5 ball or 6 ball with pentagonal symmetry, and when there are 4, they result into a cubic symmetry. If there are only 3 balls, they are having spherical atoms having interaction, one-to-one interaction, and organize themselves in different fashion when they are repelling each other.
So in this model, we have the magnetic interaction, but here in this model, we have gravitational interaction. When these steel balls are put together, they organize themselves in different arrangement. We call it as the crystalline structures, and this is how the dynamic form look like.
We have a model of solid in 2 dimensions where the spherical ball of steel are about 10,000 in number, placed between 2 parallel plates having a spacing around 1 mm. And when we see through, then we see the dense remnant painting of powder spheres as a model with a lot of defects in it. The grain boundaries, the vacancies, and dislocations are visible throughout the structure. So the solid, it shows a plane, a monatomic plane.
So using this kind of model, we can talk about the crystal structure and organization of atoms, and when they interact through the van der Waals potential. So we have got a very simple model to show the van der Waals effects is using this bar pendulum and a magnet at the bottom. If we revert that, then it comes in the equilibrium, and now it is coming in between the two. Now it is in the attractive mode, and we can control the force of attraction. So it is attracted by either one, this one or the other one. Okay, so it has 2 atoms potential, right? 2 magnetic potentials close by. So this can swing from one to another. In anharmonic oscillator, here we have got the concept of the gravitational interaction and magnetic interaction together. If I remove this one, then it is only the gravitational interaction and it's a harmonic oscillator. But here is a magnet and there is another magnet here. So this is repelling at the center. So when the kinetic energy is large, it can cross the barrier, but when the kinetic energy is small, it may not cross the barrier. There is very little damping in this setup, so that it takes a long time. I can increase the distance slightly or decrease the distance and arrive at a situation where it marginally passes and ultimately stops on either side. I don't know which side it will stop. And now it is trapped in one of the potential. So this is the video showing the same phenomena. Let me have the attractive potential with the single magnet here in place of two. Right now there is no magnet at the bottom, but if we clamp a magnet at the bottom, it could be in the repulsive. In the repulsive mode, it behaves like a circular pendulum, but in attractive mode, then at large amplitude it can swing, but as the amplitude decreases, it is trapped into the magnetic potential well, and its time period increases. So it's like bound electron, okay, electronic potential around the lattice. So using such models, we can teach the quantum science. In anharmonic oscillator, if you do a little modification by placing a spring mass system as a model for atom, then this bar pendulum behaves like a photon, and the interaction is similar to Raman's concept. What Raman says that as photon interacts with atom, sometimes the interaction is phase or sometimes it is out of phase. So this is an independent oscillator. This is independent oscillator. The interaction could be in phase or out of phase, so that the energy is transferred to this or from here to here. Okay, that is what is analogous to Stokes or anti-Stokes line, and this is how the dynamics looks like. Using a video, we can do, using a tracker, we can analyze the kinetic energy variation in the pendulum and get the spikes. In order to demonstrate the Bohr model, we have a simple arrangement of a speaker and a loop, so that with the audio frequency we can generate the waves in a strip, and they travel in a clockwise or anti-clockwise direction and result into stationary waves. And analogous to the Bohr orbital, okay, we get the condition 2 pi r equal to n lambda, and they are in the visible range. At around 15 hertz, 20 hertz, 30 hertz, we get different resonant states using such a setup. At low frequency, if we have an assembly of such simple pendulums which are connected through a strip, then the oscillating strip oscillator can transfer energy clockwise or anti-clockwise and result into the stationary state of a loop, similar to the Bohr orbital model. Here the frequency is really low, at around 1 hertz or 2 hertz. You see this phenomena. In hydrogen atom, the orbital frequency is of the order of terahertz, and that is what we talk about. The wavelength is something like Balmer series, around 2000 Armstrong. When we talk about the alpha decay, I have got a small model here. It's called linear track, and in linear track, when you see the dynamics, this apparatus has been developed by Professor Saraf at University of Rajasthan, where we are having these two magnets as a generating a potential well, and this is analogous to the motion of a alpha particle with constant energy. As it passes through a potential well, there is an interaction and energy transfer to this oscillator. So if it is in phase or it is in out of phase, that situation, this moving alpha particle could be trapped in the nucleus or can be de-trapped. So that concept can be visualized. So as it passes through, there is interaction, energy transfer, and at certain condition you will get the phenomena of trapping and detrapping. It still escapes. Now it is trapped and escapes. This is like decay of alpha particle. So alpha particle exists inside the nucleus and it decays out. The probability of decay. These are some models which student can make in their laboratory using their toys like balls, plastic balls. For example, if he wants to develop a methane molecule, then one big ball with 4 small balls at 110 degrees separation, and they are attached with a spring. And again, they are mounted on a speaker with a spring so that we can transfer a periodic energy. So this is a molecule, and we want to study the resonance state of a molecule in place of simple pendulum or a compound pendulum. Then what we do is connect a signal generator and see the vibration states. And this is analogous to the water molecule. We have oxygen and 2 hydrogen. Again, these are the bonds, and you see the dynamics, how they look like. When you adjust the frequency, at a particular frequency, the whole molecule vibrates, agitates this way. This is what we call it as a torsional mode of vibration. But when we change the frequency at another frequency, these balls vibrate longitudinally, and we have a vibrational mode or stretching mode of vibration. All of them are in phase, stretching the strip. The similar behavior can be seen in a water molecule. This is a torsional mode of excitation. And here we have the stretching mode of excitation. This is a simple demonstration of Rutherford scattering through laboratory experiment. What we have is a ring magnet placed on a circular dial, and this is a bar pendulum again, long bar pendulum with a magnet here, analogous to the positive alpha particle, and a similar pole like north pole of a ring like a nucleus, and does the scattering. When you want to change the energy, kinetic energy, you release this pendulum at different distance, and when you want to talk about the impact parameter, okay, then you place this ring in the center or away from the center and study the dynamics. So this sort of setup depicts the Rutherford scattering. Even similar behavior we can find it here. A single pole magnetic scattering. In order to see the plasma, the fourth state of matter, a simple setup, a small acrylic tube with O-ring and a rotary vacuum pump, we can generate low pressure inside this chamber, and applying a high voltage across the electrodes, we can generate a plasma inside the chamber. As the pressure reduces at around 700 volt, you see the gas discharge starts. and when there is a gas discharge, the positive ion drift to the negative electrode and the electron are collected by the positive electrode, and you get a gas discharge, and that is how the localized plasma can be generated in a small chamber, and that is what is it? Basically the fourth state of matter, where we have the neutral gas atoms and the ionized atom as well as electron. They are in dynamic equilibrium. As you change the pressure, they recombine and become a neutral. Okay. So basically the theme over which Professor D.P. Khandelwal stressed throughout, that we should have some laboratory where the student can play hands and have independent style of learning by doing. For that, we have set up countrywide the national innovation hubs, and we have developed several such models which can be used for demonstration of fundamental concepts, for quantification of some parameters, as well as they can be multiplied easily or they can be fabricated with the locally available material and can be maintained very well. Throughout the country, on the same theme, we have installed about 21 innovation hubs, right from Jalandhar, Pune, Bhubaneswar, Wardha and Bathinda recently, and more are coming up at Raipur and Bhopal, and of course the other places like Pilibhit, they already placed the order. Couple of innovation hubs are installed within the country, within city Jaipur. We have got 4 innovation hubs. The first one was installed at Vivekananda Global University, where I was as a Vice Chancellor, and we started working on this theme, and later on at IIS University we have installed this as an innovation hub, and all these facilities are here. The students are enjoying this sort of a stage show. We have got an ample place to bring about 30-40 students every time and interact with them with these fundamental or the basic apparatus. Okay. So in fact the theme which we have generated in these stage shows, that we should teach physics so that they enjoy learning through playing. So we have used the toys, we have used balls, we have used the magnets to teach the fundamental theme. Okay, in all of them the basic theme is that in quantum science the parameters are different. Here the parameters are in the visible range, and that is what is the importance of physics demonstration I have learned from Professor D.P. Khandelwal. So I am grateful for the IIPT who have given me this opportunity to express my ideas and themes before all of you, which can be shared at a different level, right from school to young one to the educated researchers or the teachers in particular at large, so that we can have a self-dependent, independent way of learning and a quality education throughout. Thank you so much. Have a good time.